So all of the scenarios that we've been dealing with so far have been pretty idealized, because essentially we've been working with particles that have had constant acceleration and then instantaneous changes between speeds and things like that, which haven't really made sense in the physical world. Okay, so you can't just have a particle suddenly changing from one speed to another, from 2 meters per second to 3 meters per second, without an intervening time when it's getting faster. Okay, so essentially all the scenarios that we've dealt with have been idealized. There haven't been any curves that we've had to deal with. It's all been nice straight lines. So here is a situation where we've got a velocity time graph, but it's not with straight lines now, it's with a curve. And what's happening is that the particle's starting from rest and it's getting faster. It reaches some kind of maximum speed, and then it starts to decelerate until it reaches rest again after 11 seconds. So what we need to do in this video is two things. First of all, estimate the acceleration of the particle at 6 seconds. So what is the particle's acceleration at that point? And then part B, the total displacement of the particle. So first of all, the acceleration. The acceleration of the graph, acceleration of the particle is based on the gradient of the curve at that point. So we've looked at scenarios where we've got to estimate the gradient of a curve. The first couple of videos in this section. Okay, so we have that skill. One thing you've got to keep an eye on is the scale of the axes here. Okay, so keep an eye on that. Now, because I'm working on a large whiteboard here, building a grid takes a little bit of time, as you can imagine. So what I've done is I've made sure that the grid is 1 for 1, so the scales on the horizontal and vertical axis are the same. So that makes my life a little bit easier. Okay? But just keep an eye out for that if you're doing this in practice. So at 6 seconds, what we need to do is draw a tangent line where either side, okay, you're trying to get the same amount of curve coming out on either side. So something like this, I reckon. Okay. So from that, I then need to draw a right-angled triangle. So what I might do actually is I might actually draw the triangle this way round. So I'm trying to make this as accurate as possible. Okay. There we go. So now I've got a right angle triangle. And what I should be able to do is measure the two sides that aren't the hypotenuse. Okay. Now, as I said, I have made this 1 to 1. So that means that I can just directly measure my lines. If this wasn't the case, I'd have to consider the scaling of those sides of the axes. But I've got myself to a situation where I don't have to worry about that. So this is about, well, it's about 20.5 centimetres. So 20.5 centimetres there. Now, of course, you could do it by looking at and saying it in terms of time, okay? But I'm just going to go with how long those sides actually are. Which way around am I going? So, this is, Is that actually 20.5? Oh, I think, no, I think it's more 20. I think that's 20 centimetres. I thought I'd fluked the same height. Okay, so the gradient is the difference in the vertical divided by the difference in the horizontal. So that would be 20 divided by 20.5. So that's 40 over 41. So the acceleration, and because it's a negative gradient as well, this must mean it's minus 0.9, let's go to three significant figures, 976 meters per second to three significant figures. So make sure you got the correct units for acceleration here, meters per second, and it's negative. So at that point you are decelerating, okay? You're slowing down. Right, total displacement. So the total displacement is the area under that graph. And what we need to do is estimate it, okay? So, there are different ways of doing this. I'm going to introduce a method called the trapezium rule in the next video. But at this stage, let's say we weren't able to do that, and I've drawn it in a grid so that I could essentially count the squares, okay? So when you're counting squares, what you want to do is you want to essentially go around the outside, looking at the squares where it is cutting through them. And one way of counting them is to include them if they are going through so that you have more than 50% included. Okay, so it might well be for this one that you go, oh well, that's about over 50% or just about, so I'll include that one. Okay, now there's got to be a bit of give and take here, and the reason why you would include some and not others is because, well, if I include this one, then that's going to be offset at some point by, let's say, this one. I won't include that square. Okay, so surely as I go through, the errors will kind of even out. So that's really the idea here. So let's say I include that one, just about, I think. I'll include that one. I won't include that one. I'll include this one. This one, it's right on the edge, isn't it? It's about 50-50. Shall we include that one? Okay. We could say that that one and that one are about 50% each. Include those as one whole, if you like. But let's just include them as wholes for the moment. This one I won't include. This one I will. This one I will. This one I won't. So any that are full squares, I'll definitely include those. Okay, that one I will. That one I won't. That one I won't. This one, you see, I think I'll include that one, but I won't include that one. Okay. That one I'll include. This one I don't think is quite 50%. I'll include that one and that one. Definitely all of those. Okay, this one, yeah, I'll include that one. Not that one. That one, yeah, that one, that one. That one, not that one, and not that one. Okay? So, I count up how many ticks I've got, and that should be the amount of meters, because it's 1 to 1, right? So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, and 1. So 10 plus 8 plus 8 plus 6 plus 6 plus 4 plus 3 plus 1. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And so that's getting me 46. Okay, so each of those squares is meters per second times seconds. And so that gives me meters. And so it should be about 46 meters. Okay? How can you make that more accurate? You could make the squares smaller. Okay, so you're counting up more squares. Or, as I said, you could use a method of finding the area under curves, such as the trapezium rule. Okay, you could also subdivide it up into rectangles, thinking about it that way, but the trapezium rule is often more accurate and quicker at doing that as well. So we're going to look at that in the next video.